let's talk now about the blood. Moving into a new system. What we're going to be talking about here for this lecture and then into the next unit is our what we call cardiovascular system. Okay, your cardiovascular system consists of three interrelated components, one of which is your blood, okay, which flows in and out of our heart. And then when it comes in and out of the heart, it uses our blood vessels, okay. The entire function of the cardiovascular system is to deliver nutrients and eliminate wastes from tissues throughout the body. And that's because most cells of our body cannot move around to get those nutrients like oxygen and glucose, and cannot travel to the dump sites like our lungs to exhale CO2 and our kidneys to excrete out, things like urea in our urine. Okay. Aside from blood, there's another fluid that helps us meet the needs of this process. Okay. The other being interstitial fluid. Okay. We've talked about blood before. Thinking back to the very beginning of the semester in Unit 1, we learned that blood is a liquid connective tissue. It's made up primarily of two things: liquid matrix or plasma that dissolves and suspends the other major component, which are the cells and cell fragments. Okay. Interstitial fluid is fluid that bathes our body cells and therefore is what surrounds them. It's formed when fluid diffuses from our blood into the surrounding areas or the areas surrounding our tissue. So in other words, what we see is the fluid and some of the other stuff within the blood leaves the blood vessels, coming into the interstitial space where it becomes interstitial fluid. Okay. Then it can be taken into cells, becoming intracellular fluid. Okay. Keep in mind that that fluid never stays stagnant, nor does any fluid throughout the body. So that fluid can then leave the cells, becoming interstitial fluid again, and then go back into the blood and become part of the blood again. So it's a nice circular series of events. So it's a nice cycle of this flow. Okay. Overall, the functions of your blood include three things: transportation, protection, and regulation. And I've got examples of each of them. The primary function of your blood is to transport different things. For example, it carries oxygen from our lungs to all the body's tissues. Carbon dioxide or CO2 is going in the opposite direction from those same tissues to our lungs. Nutrients are picked up from the digestive tract. Metabolic wastes are carried to the kidneys to be filtered out and made into urine. Hormones, which we just got done talking about, are carried to target cells. And then stem cells can be carried from bone marrow to our various tissues. Blood provides protection in a variety of ways. It's involved with a non-specific defense mechanism known as inflammation. This is what occurs whenever we have some type of tissue damage, whether it's a cut, a sprained ankle, or something more severe. The various white blood cells are going to provide immunity through their various mechanisms, which we'll find out about. Antibodies produced by a certain type of white blood cell help neutralize toxins and pathogens. And then platelets, which are very important for blood clotting whenever a blood vessel is broken and we start bleeding. And then blood helps regulate things like fluid distribution by moving the fluids across the capillaries. The proteins in our blood help to buffer and stabilize the pH of our body, so keep our acids and bases in check. And then we help regulate body temperature by transporting blood to skin or to our visceral organs, which sounds kind of weird. How can you regulate body temperature by moving your blood? Well, think of it simply. Heat builds up in the blood, and if you bring that heat closer to the skin surface, it is more likely to be dissipated to the exterior. That's why when we get hot, our face becomes more red. We are distributing that blood closer to the skin surface, because then, you know, like the air that flows across the skin surface, whether we're fanning ourselves or it's just a breeze, that helps cool the blood. Also, the skin is where the sweat is, and that helps cool the blood internally. When we get really cold, we try to prevent the blood from getting too close to the surface of the skin, and that's where we're going to reroute it to our internal visceral organs. And that explains why places like our fingers and our toes, our ears and our nose look more white in appearance, because they're not having as much blood flowing through them. And they're also the places that hurt and are most susceptible to frostbite. Okay. Looking at the picture here at the bottom, this is the exact same image that we saw in that tissues lecture, which is a smear of blood, looking at it under a microscope 400 times. So we can see we have lots and lots of these red blood cells or erythrocytes. Okay, those are the most prominent and actually most numerous cells in the entire body. Then you've got these bigger cells called white blood cells, and there's 5 different types of them. We see a couple of them labeled here, leukocyte, neutrophil, and then down here, monocyte. These little specks here are the platelets. In between those cells is the plasma. As far as the image goes, and actually this is the only lecture all semester long where there will be not a single picture on this segment. So there will just be 20 traditional questions, multiple choice predominantly, but not a single picture from this segment on the exam. All right, let's talk a little bit more about the plasma of your blood. And then down here at the bottom, we'll talk just briefly about the cells and cell structures. All right, as a whole, we can describe our blood as being denser and more viscous, or a little bit thicker. That's what the word or phrase more viscous means. A little thicker than water, has a slight sticky feel to it. Temperature is about 38 degrees Celsius or 100.4 degrees Fahrenheit, which is about a degree C higher than oral rectal body temperature. Has a slight alkaline or basic pH. Right around 7.4 is what we like to see it at. So somewhere between 7.35, 7.45 is where we like it to be. If you don't know what the pH scale is, 7.0 is neutral. Anything below that is an acid. Anything above that is a base. And 7.4 therefore is a base, and it's a very, very weak base, but it is a base nonetheless. Okay. Healthy young female will have about 4 to 5 liters. Males will have about 5 to 6. If you think about like a big pop bottle, you know, about 2 to 3 of those. If you're talking about a man, is how much you're going to find in the body. So not a ton, but that does represent about 8% of your total body mass. Okay, which is what we can see here in the kind of schematic on the left side of the page. Whole blood up here in kind of the peach shaded portion is 8%, and that leaves 92% other stuff. Now, of that 8% of our body, that whole blood has 2 major components, as we've already said, the plasma or liquid portion, and then the formed elements. Okay. Plasma is just the clear extracellular matrix or fluid portion of our blood, and it constitutes about 55% of our total blood volume. So a little bit over half of our blood is the liquid. Okay, so just about half or a little bit more than half when you are bleeding of that blood coming out is just the liquid part. And most of that, just like any fluid in the body, is water. About 91.5% of your plasma is water. So just about half of your blood you can think of as water. Then you have about 8.5% of things dissolved in it, which are primarily proteins. And those plasma proteins include the following three major classes: albumins, globulins, and fibrinogens. Or excuse me, fibrinogen. It's just a singular one. Albumins are the most numerous. They're produced by liver cells and function as transport proteins for several steroid hormones and for fatty acids. So think of albumins as kind of like an Uber where they carry steroid hormones and fatty acids in our bloodstream. Globulins are the second most numerous. There's 38% of the plasma proteins falling in this category, roughly anyway. Also produced by liver, but also in some cases produced by plasma cells, which develop from a type of white blood cell known as a B lymphocyte. Okay. There's actually three types of globulins. You've got alphas and betas, and then gammas. Okay. Alphas and betas are very similar to albumins in that they are transporters of things like iron and lipids and fat soluble vitamins. So they are kind of like an Uber. More important, in my opinion, not to say that the others aren't important, but gamma globulins are very, very important because those are the antibodies of our body. Okay. So they function with immunity in mind, helping neutralize toxins and bacteria and viruses and whatnot. Fancier term for antibodies is immunoglobulins, and they are called immunoglobulins because they're immune in function, and then globulins, as you can see. Why? Because they're from the globulin class. And then finally, fibrinogen is the last major plasma protein. It's the least numerous, only around 7%, also produced by liver, but this is a very important protein in that it helps us form a blood clot. And for those of you who are in physiology, you'll have that to look forward to because we talk about forming blood clots, not so much in this class. There are other plasma proteins, but they only represent about 1%. That includes various enzymes and hormones as well as clotting factors. Okay. But then you've got a host of other stuff dissolved in the blood that includes electrolytes. So this is what you hear about like when you watch Gatorade commercials. These are just ions like sodium, potassium, calcium, magnesium, chlorine, bicarbonate, sulfate, and hydrogen phosphate. Various nutrients, glucose, carbohydrates, amino acids, lipids, cholesterol, hopefully not too much of those floating in our blood. Gases, oxygen, carbon dioxide, but also even nitrogen, and then a host of waste products, which includes urea, which is formed from the breakdown of proteins, creatinine, which is formed from the breakdown of creatine phosphate, and that occurs in our muscles, uric acid, which is from the breakdown of nucleic acids like DNA and RNA, and then bilirubin, which is the breakdown of hemoglobin. Okay. You probably remember back at the beginning of the semester when we talked about the skin, we talked about like skin coloring, talked about jaundice. I remember where you can get yellow, and the reason that people turn yellow actually has a lot to do with the bilirubin and the breakdown of hemoglobin and stuff. If you ever heard of gout before, gout's a very painful joint disorder. It's because the body's not getting rid of enough uric acid. So we're not getting that stuff out of the blood. It can be detrimental to your health. So that's a little bit over half of your blood, which means a little under half of our blood, about 45%, are the formed elements, which have a visible structure and represent cells and cell fragments. Okay, the most numerous of which are your red blood cells. Now, keep in mind, here in this illustration, it says 4.8 to 5.4 million. Does that mean that's what we have total in the body? Absolutely not, because what we see here is actually per microliter, and that's a very small sample of blood. Okay, if you want to have your mind blown, how many red blood cells are in the human body? Okay, 25 trillion, according to whatever that website is. Okay, that accounts for about 80% of the cells in your body are these red blood cells. So by far and away, the most numerous cells in our body are these red blood cells. We'll talk about those more on the next page. Okay. Then you got the 5 different types of white blood cells: neutrophils, lymphocytes, monocytes, eosinophils, basophils, each of which has a unique set of features and unique function. Okay. And then platelets, which are actually not even a cell, but they form when cells called megakaryocytes kind of break up into pieces. We'll see that here in a couple slides. Over on the right, a couple more images. This is a pretty cool view of those three major formed elements. Here you can see a red blood cell, very nice and red. There's a white blood cell. We can see some platelets. This is all zoomed in under a microscope 3,500 times, which your naked eye can see. Over here is a picture of what would take place to your blood if it was centrifuged, which a centrifuge is a machine that spins like a vial of blood. Like here you see a blood sample in a test tube. It spins really fast. And in doing so, it helps separate the blood into its different components. At the bottom, you can see is where the red blood cells are. Then you have a thin, what we call buffy coat, where the white blood cells and the platelets are. And then sitting on top would be the liquid plasma portion. You've probably heard of people donating blood. You can also just donate your plasma, which is kind of a cool process. You find plasma centers a lot of times in college towns because they actually pay money, and they like to take advantage of the fact that college kids a lot of times are broke. I know there was one in Manhattan, not too far from K-State, where I went to school. There was one in Lawrence. I know my brother-in-law, both of them actually went there from time to time. It's a pretty cool process how it all works. They stick a line in your arm, just like if you were to donate blood, the traditional way where, you donate a whole sample of blood. But in the case of donating plasma, that line draws that blood out into a machine that has the capability of separating the plasma from the formed elements. So the plasma collects in a bag, just like your blood sample would, but they are able to re-inject the blood cells and the platelets back into your body, which is really cool because that then enables you to donate plasma actually a couple times a week. Whereas if you donate whole blood, you have to go like, I want to say like 2 months before you can do it again. As you can see, and what I've already mentioned, most of your plasma is water. And so you can donate that plasma and replace that without too much trouble. But plasma is very beneficial. They use it for a lot of different things, making medicines and whatnot. And then obviously people that donate whole blood, that's useful for like transfusions and that kind of stuff, which obviously is a benefit to a lot of people in need. All right, done talking about the plasma. Let's talk a little bit more about those blood cells, starting with the red blood cells. Fancier term for that are erythrocytes. Typically, I just call them red blood cells, or RBCs for short. Let's see, some more links. Is this heme the last blank? Or is there okay. Out there. All right, red blood cells make up about 98 to 99% of the formed elements. And as we just learned, there's 25 trillion of them. And they have two principal functions. They pick up oxygen from our lungs and deliver that oxygen to the tissues of our body. They also help pick up carbon dioxide from our tissues and deliver it to the lungs to be exhaled out. Okay, they are very small in size. In fact, I think they're the smallest cells in the body. If they're not the smallest, they are among the smallest. They have a unique structural makeup. Okay, they have a very nice rounded shape to them, as we saw on the previous page, but they are going to be kind of concaved in feature because the fact of the matter they have no red blood, or they have no nucleus. Okay, there is no nucleus, and there's actually not most of those organelles that we learned about previously inside, and that's why it indents like it does. Okay, we'll learn about its kind of life cycle and how we get to that point here towards the end of actually at the end of the lecture. Okay, the reason that it has a lack of a cell nucleus in most of those cell organelles, because it maximizes its volume so that it can carry more oxygen, carbon dioxide. Okay, that essentially means that it's a more of an empty room, so it can store more oxygen and carbon dioxide and carry it that way. Okay. Several proteins are associated with red blood cells. The inner surface of a red blood cell is composed of two proteins, spectrin and actin. Yes, that's the same type of protein that we previously learned about in our muscles. Okay, but these are very important for flexibility and durability that our red blood cells must have. Here is a picture of some real life red blood cells passing through a capillary, which is the smallest type of blood vessel that we have in the body. And as we've just described, there are trillions upon trillions of these red blood cells flowing through the body. And a lot of times they're flowing through capillaries, which are just about the same width as the red blood cell. And so there's a lot of pushing and shoving. It would be like if, a host of people, like 20, 30 people were trying to move through the same door at the same time. There'd be a lot of pushing, shoving, beating up on one another. Okay. Unfortunately, because they have no nucleus in most of those organelles, they kind of get beat up and can't fix themselves. So their lifespan is only about 120 days before they start to break down, and as they squeeze through those capillaries, as well as their inability to replace damaged and worn out cell structures. Once again, no nucleus in most organelles. So that's what happens. They just start to break down, but that's okay. They can be removed from our plasma and replaced pretty easily. Okay. Looking at this illustration, we show the makeup of what we call hemoglobin. Hemoglobin is about 33%, or about a third of the solution of the cytoplasm of our erythrocytes. So about a third of the interior of red blood cells made up of hemoglobin. That amounts to approximately 200 to 300 million molecules per cell, which, that's a heck of a lot of hemoglobin. This is a molecule that allows for the transport of oxygen and carbon dioxide. Okay? It carries about 98% of the oxygen in our bloodstream. Okay? It doesn't combine with carbon dioxide and carry it, as predominantly only like 23% of your CO2 binds to hemoglobin, but it does carry carbon dioxide. Now, there's two major parts to hemoglobin, literally heme and globin, which is where its name comes from. Okay, the globin part of the molecule is what we see here in these kind of blue squiggly lines. It might not look like there's multiple lines, but there's actually 4 of them. Okay, each of those are a polypeptide chain, 2 of which are alphas and 2 of which are betas. If you look really hard, you can kind of see there's a darker blue color and there's a lighter blue color. The 2 lighter blues are the 2 alphas, and then the 2 darker blues are the betas. Not that that really matters. Okay, that's the protein part of hemoglobin. Associated with each of those 4 chains, it kind of looks like a flying saucer or UFO. Zooming in at one of them, we can see it here, is what we call the heme. Okay, heme is not a protein, it's a non-protein pigment. But at the center of each of those, and that's shaded red here, and we can see them in all 4, is a ferrous iron, an Fe2+. Okay, this is where an oxygen, an O2 molecule, can stick to the hemoglobin. And therefore, since there are 4 of these hemoglobins, or excuse me, 4 of these hemes in the hemoglobin, that means each hemoglobin molecule can transport 4 oxygen molecules. So if you take that 4 oxygen molecules times 200 to 300 million molecules per cell, okay, and you multiply that by the trillions upon trillions of red blood cells in our body, that demonstrates just how great our blood is at carrying oxygen. Okay, And hemoglobin is also involved in regulating blood flow and blood pressure by releasing a hormone called nitric oxide, which is a local hormone that promotes vasodilation and improves blood flow and enhances oxygen delivery. But as I mentioned, hemoglobin's primary job is to carry oxygen. The final protein in our red blood cells is called carbonic anhydrase. It is an enzyme that catalyzes or speeds up the reaction joining carbon dioxide and water, forming an acid called carbonic acid, which then dissociates to form bicarbonate ions. And bicarbonate ions are very, very essential for maintaining normal blood pH levels. So got several proteins, carbonic anhydrase, hemoglobin, spectrin, and actin, all within our very tiny little red blood cells. Okay. All right, moving on. Let's now talk about our white blood cells. As I've already said, there are 5 of them, each of which is unique in structure and function. Maybe you want to go ahead and fill out that bottom blank so we don't have to worry about it later. All right, let's talk white blood cells. Let's go by the term leukocytes, which are formed elements in our blood providing protection against infectious microorganisms and other pathogens. So it protects us from things like bacteria, viruses, like coronavirus or COVID, whatever you want to call it, but also like fungi, parasites, even like worms, unfortunately, can be, become inside of our body, can infect us, as well as, certain drugs, certain chemicals that can be detrimental to our health. Okay. White blood cells differ from red blood cells in that they retain their organelles throughout their life, so they still have the nucleus at the center, along with several other organelles. We can see that all in the pictures there in the middle of the page. What you do not see in white blood cells is hemoglobin. So white blood cells have no role in the carrying of oxygen or carbon dioxide. Now, we classify our white blood cells into 2 categories, and it's based on what they look like under a microscope. Okay, what you do is you'll see them either appearing nice and like speckled, or they almost look like they have freckles. Okay, we call those the granulocytes. Now, your textbook, you'll see them listed as granular white blood cells or granular leukocytes. Okay, granulocytes, granular leukocytes are the same thing. Those are the kind of speckly looking ones, and they are the first 3 shown here in the picture, and those are the first 3 that I have listed off. If you notice, they all are similar in their name and that they end the same way with the suffix "phil" or "phils" if you're talking plural. Okay, so the phils are always going to be the kind of grainy, speckly ones. Okay, and it's all about the absorption of different stains. That's done when preparing the slides to view the blood. Okay, let's talk about the different types. Neutrophils are the most prominent of our white blood cells, contain an S or C-shaped nucleus with 3 to 6 lobes. And I guess you can kind of see the S shape to it. You can kind of see the different lobes for sure there in the picture. Their granules are small and poorly absorb both basic and acidic stains. Not that I really care about that. Definitely want you to highlight this sentence here. They're the first leukocytes to arrive at an infection site responding by chemotaxis to chemicals released by damaged cells. So these are the first responders. Okay. They are also important phagocytes, which if you want to kind of just visualize what phagocytes are, those are cells that can basically gobble up like viruses and bacteria and digest them. So think of these guys like Pac-Man, and then they can run around and swallow things and digest them. Okay. So they're very important. They are especially important for destroying bacteria using several chemicals. After performing phagocytosis, neutrophils are usually destroyed by antibiotic proteins, which results in the formation of pus, that whitish material. You think about like zits and that kind of stuff, but it's dead neutrophils plus just other dead tissue. Eosinophils, very small number, only 2 to 4%, contain a bilobe nucleus. Here you can see the two lobes very nicely. They're connected by a little strain of chromatin. Their granules stain red with acidides and kidney digestive enzymes. I'm not really worried about that. But I do want you to know the last little bits here. They combat the effects of histamine and allergic reactions. Phagocytized complexes formed by the action of antibodies on antigens, which are just anything that's foreign, and they can destroy certain parasitic worms. Basophils are the least numerous white blood cells in the body, only 0.5 to 1%. Have a U or S-shaped nucleus with 2 to 5 lobes connected by strands of chromatin. They look like mast cells, which are found only in connective tissue, but their granules contain 3 chemicals, histamine, serotonin, and heparin, which are released in response to tissue damage and pathogen invasion. Basophils are kind of annoying, and I say that, which is kind of going to sound weird because they help protect us, but sometimes they get a little overzealous in the release of histamine, serotonin, and heparin, especially the histamine that they release. These guys are a big contributing factor in allergies, and why we get sneezy and itchy and red. A lot of it is because of the histamine that's produced by these guys, as well as mast cells. Which explains why if you have allergies, you might take an antihistamine, and you'll find that in like Allegra and that kind of stuff. All right, agranulocytes. Remember, A at the beginning of a word means the opposite or not. So these are white blood cells that are not grainy or speckly in appearance because their cytoplasmic granules are scarce or absent. Nucleus of these guys is typically not lobed. Notice that the ending of their word is very different. It's not phils, but it's site or sites. Okay, and that includes lymphocytes and monocytes. Lymphocytes, about 1/4 of the white blood cells of our body, often classified as small, medium, or large, contain a circular nucleus, and you can see that very nicely here in purple. Almost takes up the entirety of the cell. There's just a very little bit of cytoplasm surrounding it. Okay. Key feature of these guys is that they're the only white blood cells that return to the bloodstream. Okay. Once the other cells leave the bloodstream, they never come back. These guys, at least some of them can, which explains why sometimes these lymphocytes can live for years. Okay. If you want to understand the importance of lymphocytes, you can describe them as the major soldiers of our immune system. And they occupy places like our lymph nodes, our spleen. They are very, very important, not just in our blood, but other places as well. There's 3 types of lymphocytes, but 2 of them really are the most prominent, T's and B's, which, if you think back to the last lecture, I was talking about T cells. T cells, just a shorter version of the word lymphocytes, so T lymphocytes. It's easy to remember where those mature, which is in the thymus, T for thymus, okay, which we were just talking about. We learned that the thymic hormones help with maturation of the T cells. B lymphocytes, whereas T lymphocytes mature in the thymus, B's mature in your bone marrow. So think B for bone marrow. The third and final type are natural killer cells, which sound really cool. They almost, to me, sound like a spy or something like that. But they aren't as really as important as the T's and B's. So what do the T's, B's, and natural killer cells do? T cells attack any aberrant cell. Aberrant would be just like an abnormal cell. So cells that are, in the tumor, cells that have been transplanted with an organ, in any cell infected by a virus. Excuse me. So that's what T cells do. B cells respond to circulating antigens, things like toxins, viruses, bacteria, by producing or dividing to produce plasma cells, which are the actual factories that produce the antibodies. So B cells result in the formation of antibodies. They don't form them directly. They have to first transform into plasma cells, which are the ones that actually do the formation of the antibodies. And then natural killer cells attack a wide variety of infectious microbes and certain spontaneously rising tumor cells. Cool thing about T and B cells is they have a memory, which explains, the benefits of like getting vaccine, which is obviously a hot button topic anymore, but it also helps with explaining why, like, when I was a kid, you got the chicken pox, you typically only have it once because your body can respond a second time much more swiftly and take care of it before a true infection arrives a second time. All right, then you got monocytes containing a large kidney-shaped nucleus surrounding a large amount of blue-gray staining dye, cytoplasm. When they leave the bloodstream and move into tissues, they enlarge and become what's called a macrophage. And you've heard me talk about those before. These are like the largest of our Pac-Man cells. They're phagocytic, which is just like what we saw, and I was describing with neutrophils, and that they gobble stuff up and digest them, so they can engulf microbes and cellular debris. And then finally, our last of our formed elements are platelets, which also go by thrombocytes. I mentioned earlier, they're not cells, but they're small fragments of marrow cells, which we see one here called a megakaryocyte. Okay. As we can see, if I zoom in, each of these little speckles kind of flaking off of the bigger cell is a platelet. Okay. A platelet is an anucleated cell fragment, so it's not nucleated. It does have a few organelles, and it's surrounded by a plasma membrane. Okay. They have a very short lifespan, only about a week before they need to be removed by macrophages in our spleen and liver. But during that week, the 5 to 9 days, they are very important. One of the most important things they do is they help with the stoppage of a blood loss when a blood vessel is broken, forming what's called a platelet plug. And they release granules that help promote further formation of a blood clot, which is stuff I get into physiology, as I mentioned already. All right, once again, no images to worry about, so we'll just move on. Final page here, I just want to talk about how we form and where we form our various blood cells, which we've talked a little bit about before. Thinking back to when I first introduced bone marrow, we learned that there was 2 types of bone marrow, red bone marrow and yellow bone marrow. Red bone marrow is the important place of our body where we undergo the production of our blood cells. As I've already said, some lymphocytes do have a lifetime measured in years, but for most of the formed elements of our blood, they last only hours, days, or weeks, and therefore must be replaced continually. Okay, we've seen these terms before, but the production of our blood cells is called hemopoiesis or hematopoiesis. Before birth, and this is way before we have any organs develop, it takes place in what's called the yolk sac of an embryo. Okay. Later, once we do have some organs, it takes place in places like the liver, the spleen, the thymus, and our lymph nodes. Okay, but then just in the last trimester, the last 3 months before birth, the red bone marrow becomes that primary site, and it continues as that site through the rest of our life. And therefore, as adults, which we're all in at that stage now, our red bone marrow is where we're making our blood cells. Okay, once again, we've talked about red bone marrow before. It's a highly vascularized connective tissue found in the microscopic spaces to the little trabeculae of our spongy bone. We find a lot of red bone marrow in the bones of our axial skeleton. Remember, that includes the bones up and down our spine and our skull, but also places like the pectoral and pelvic girdle, so like your hip bones, your clavicle, your scapula, the proximal epiphyses of the humerus and femur, so up there by your shoulder and up there by your hip. Okay. Within our red bone marrow, we find pluripotent stem cells called hemocytoblasts, or as they're just labeled here, pluripotent stem cells. They have the capability or capacity to develop into many different types of cells, and these cells then reproduce, proliferate, and differentiate into the cells that give rise to our different blood cells. And you can see down here at the bottom, all those blood cells are listed. Red blood cells, megakaryocytes that form the platelets, the different white blood cells that we can see, eosinophils, basophils, neutrophils, monocytes, which we learned become those big cells called macrophages. Here's our T's or B's and our natural killer cells, which are the 3 lymphocytes. B cells, remember, are going to form plasma cells, which are the ones that produce the antibodies. Okay. But also forming from that original pluripotent stem cell, and they're not shown here, but that includes reticular cells, which are found in our lymph nodes, producing reticular fibers, mast cells, which actually we can see down here, which we find in our aerial or connective tissue involved in inflammatory responses. We can also form adipocytes or fat cells, osteoblasts in our bones, chondroblasts in our cartilage, and muscle cells obviously in our muscle. Okay. Once the blood cells though are produced in the marrow, they enter the bloodstream through sinusoids, which are capillaries with large holes or sinuses in them, where they can then begin maturing and functioning. Once again, no image on this segment of the exam, so don't worry about this complicated image. Just wanted to kind of include it so you can kind of see how we go from one original cell to all these other cells. I promise you, you can see where that distinctive shape comes from for a red blood cell, how it has that indented feature. And I mentioned it's because the nucleus is removed, and it takes place during that development where it's what we call a reticulocyte, which is a precursor cell to the red blood cell. So there you can see it as promised. All right, any questions here?